Hey friends, it is Ben again. This is a video for Wednesday, April the 20, I guess it'll be the 26th. Hopefully you will have watched it before we get to class that day. Um, what we're taking a look at today is the notion of using hypothesis testing. And in particular, we're going to look at some simulations where we're making the computer produce fake random samples and seeing what kinds of results that we would expect in different situations. Okay. And so let's kind of launch into that and talk about what's going on in the notebook itself. What I would advise you to do is to pull up the notebook in another window and kind of come back and forth and make yourself some notes about what I'm looking for. I've tried to mark the individual problems with problem 1, 2, 3, and so forth. If there's something that's not necessary, but you should try, if you have extra time, I'll give you some extra credit for going ahead and doing that, and it'll be marked with a plus. Okay. So let's, yeah, I started to do something the wrong way. Let's share screen and we will go over to that, and I'll have to take off these glasses because I can't read with them on. So here we talk about the tests for the population mean mu. Okay. So the situation that you've got is that you have pulled some kind of a sample from a population. Okay. Because of the numbers I've got floating around here, maybe you have random sampled a bunch of test scores from students who were taking statistics. And you want to see whether the mean ends up being more than 70. Okay. Maybe it's a 100-point test and you're trying to look and see whether it seems like the average student passed that test. Okay. Got a C- or better. So that's kind of the strategy of what's going on here. Now, to explain a little bit, we are always thinking about these hypotheses. Hypotheses are statements of facts about what's going on, and we are treating them as though they're math hypotheses. So here, for instance, we have the null hypothesis that mu, the average student score, is 70. Okay, that's the null hypothesis. And we want to disprove that in favor of the alternate hypothesis. Can I make that a little bigger? Yeah. The alternate hypothesis of mu being greater than 70. Okay. So, um, so the notion then is that if you've got a sample that's in that kind of direction, then you can do some testing. Let me actually show you a picture that's, yeah, I'm about to do it the wrong way again. Let me show you a picture that is associated with this sort of thing. Okay, so this is on the TI calculators when we're doing some sort of a test and we want to show that something is more, then the notion is that we put the thing, the average that we want to show it's more than, in the middle of a distribution. And from the data, we have to have some idea of how spread out the distribution is. And then this area over here is showing us the probability that we would get the sample that we got, that we get that sample mean and sample standard deviation, given that we had that mu in the middle. Okay. So the one I've got on the calculator is not the one from what we're doing as an example here on Python, but it shows a p-value of 0.0978, which would say that you have a 9.78% chance of getting a random sample that looks like this when your mu is actually the value of 70%. So getting about a 10% chance of having this happen, that's not really that unusual. Once it gets under 5%, we start saying, it's probably unusual enough that we think that we've got strong evidence. Okay. So that's the idea of what we're doing. But we're going to do it through Python and have it handling data. The reason we want to learn how to do it through Python instead of having to do it through the calculator is because of our data sets. If you remember, the vehicles data set had 45,000 entries in it, right? Your calculator would require you to type 45,000 entries to get that done, and you can't. So if you're going to work with big data or even moderately large data, you have to use something where you can program and let it do it all in the background. Okay. So we're going to go back here to the notebook that we're looking at, and we're going to do an example of seeing what happens here. So as you'll see, I'm importing numerical Python, NumPy as NP, and then I'm going to import the normal distribution from Skippy, okay, the scientific Python statistics package, right? Now with that norm package that's here, it has a super convenient thing of just saying RVS for random variable sample. And we're going to do it with a mean of 75 and a standard deviation of 12. Those are just the settings that we're going to have on this. For me, from a statistics class, which I said was kind of what we're thinking about on this, an average of 75% and a standard deviation of 12 is about a normal kind of distribution to have. No puns intended, okay? Okay, the pun was kind of intended, but you know. Anyway, though, the size of my sample is going to be 30, and so this will just pull 30 numbers there. And if you want to, you can then print out and see the sample and see what it looks like. I don't remember whether we did that here. I think that was on the stuff that we did yesterday, that we looked at a sample to try to see whether it was approximately normal. But here we're going to trust that it's approximately normal because we pulled it from a normal distribution. Okay. And then I went ahead on this sample here and rounded everything to the nearest integer because, you know, it's test scores. It doesn't make sense to have them be a bunch of decimals. And then the low sample, I went ahead and did a random variable sample from that. And this time I made the mean, which they just use LOC for that for some reason, but I made the mean be 68 and the scale be 12, okay? So that means it should be less than the 70, okay? So, and then I rounded it again, right? So with the thing that we're going to do next, we're going to look at the high sample and see whether we've got significant data that says that it's higher than 70. Okay. Yes, I know the average that we get, since we pulled it from something with an average of 75, the average ought to be 75. Okay. But by random chance, sometimes we can draw something that's not that. Pretty low possibility, but it could happen. Okay. Anyway, though, so I took Skippy here and I imported this package called, or this function called t-test1sample. Okay. As you might guess, there's also a t-test2sample. But when I tried to use just straight out z-test, it didn't seem to know about it. And that might be that I just haven't found the right name for the package or something. But in any case, this is set up to have a single sample and you're testing to see whether it's bigger or smaller than something. So here I say my result is going to be a t-test, one sample. I feed it that sample that we made in the previous cell. And I tell it the population mean that I'm testing against is going to be 70. And the alternative is I want to see if this is greater. Okay. And so it will do whatever magic it does and put the result here under result. And then I told it to print the results p-value. So you're able to take the result, and the result has like several different pieces to it. It has a p-value and a t-score, a t-value, and maybe some other stuff built in as well. Okay. But in any case, we asked it to print out the p-value here. And for that particular sample, it got it being 0.000178. Okay. So that is around 2/100ths of 1%. That's very much smaller than 0.05, right? So this is a super duper strong evidence that the stuff we were pulling, the random sample, is in fact from a population with a mean more than 70%, which we knew because we had one that we pulled it from a population with 75% as the mean, right? But this is showing us how the process will go, okay? If you've got some other population that you pull and you don't know, if you get a p-value that's super duper small like this, that tells you, yeah, the mean was larger than 70%, okay? So then for this next part here, I forgot what this next part is. We're going to check out the low sample, right? And for the low sample, we do the same thing. We say, t-test it. Here's the low sample. My population mean is 70. My alternative is the greater than, even though we know it'll be less than. And then the p-value it comes out with is 0.3726-ish, okay? More than 5%. So that means that the evidence that we have for this sample is not a strong indicator that we've got something that's more than 70%, okay? If we had pulled something there that was that had a mean of 71%, and the sample size wasn't like huge, we would similarly get a p-value that was more than 5%, but it might not be that much more, okay? But so anyway, p-value, you're always looking, is it more or less than 5%? That's just kind of the rule of thumb. Although medical applications tend to do 1%, or I've seen a couple of medical applications that have even smaller significance levels than that. Okay. All right. So in any case, though, that was the indication that we didn't have strong evidence there that the low sample was higher than 70%. Okay. Keeping in mind, real data, you wouldn't know the population that it came from. You would just be saying, I need to see whether it's strong enough evidence. And that's all this does, is tell you how strong your evidence is. And the smaller the p-value, the stronger your evidence is. Evidence that's in the 37% range, not good at all. It is in fact bad. You may be hearing my cat meowing. He thinks that I need to go pet him or something. I don't know. Okay. But if you get something that's less than 5%, we consider it to be strong evidence. And like the one that I got earlier that was way less, it was super duper strong evidence. In fact, such strong evidence that you might suspect that I faked my data. And so, which I did. All right, so problem one here, I want you to take the code that I used to make the high sample there. And let's see, I want you to create a new one and experiment with changing the value of LOC. So change the value from 75% to to something else, and play around with it, execute it several times, and see what goes on with the statistical significance of the p-value. When you get, how close can you get that LOC to 70% and still have significant evidence, right? Now, keep in mind, because it is random sampling, you will get sometimes you will get different p-values when you have the same code running, because it is randomizing. Okay. Then for problem 2, I want you to take that same set of code. You can even use what you've got there. Copy it down here and leave LOC as 75, and then decrease your sample size. We were pulling a sample size of 30. That's kind of our default smallest sample size that we usually use. But pull some smaller sample sizes and see how small you can make it and still be getting a p-value that's significant most of the time. Okay. So, and then problem number 3, if you remember from the previous days, the Tuesday's assignment, it had you pulling in the vehicles data, and I think we had pulled out, we pulled out information for Kia, just one of the car manufacturers, and we discovered that their highway mileage data looked to be approximately normally distributed. Okay. So what you're going to do here is to test the hypothesis where you think maybe the mean highway mileage from all the Kia cars put together would be less than 30 miles per gallon. Okay. I don't remember what the numbers are for it, but if you get an X bar out of it, a mean that is, which, you can pull the data and just say, this column dot mean. If you get a mean that's more than 30, this is going to be a bad hypothesis. Okay. If we got an X bar that's 31, 32 or something, there's no way that this will be strong evidence. Okay. And you would be able to just stop there. But I believe you're going to get a number that's less than 30. If it turns out that you don't, say something to me about it. We'll change the hypotheses and in order to just get an example that works. Okay. But I want you to take something that's real data and do a hypothesis test with it. Just see if you get strong evidence or not. Your sample size on that should be pretty large, so I think you will. Okay. All right. So our next bit that we're looking to do is about a population proportion. And we're going to use pi, because if we don't use a different letter, this gets super confusing. All right. So pi is the Greek letter that makes the P sound. So we're using pi instead of P. I hope that's okay. But the notion here is that we have populations where they have, where you're trying to identify a certain characteristic. I have 3 children and 2 of them have red hair. Okay. And if you talk to red-haired people, occasionally they will tell you this story where they've heard that red-haired people are dying out and there won't be any people with red hair in the population. Totally not true. Okay. It's like, well, amongst Caucasians, red hair is about 8%. I don't know what the percentage is amongst Africans, people of African descent. And those people of Asian descent, it's pretty close to 0, but it just has to do with where that gene originated and whatever. It's totally to the side. But if you were wanting to test something about a population of how many people had red hair or something, you might be interested in taking a sample, maybe looking at a particular town and saying what the proportion of red-haired people is there. If you do that in Ireland, you'll get a higher percentage than you do if you do it in Spain. Okay, just examples there. Okay, so this example I've got here, I think I'm talking about flipping a coin or something. Nope, this one is about voting proportions, right? So voting proportions, it ends up being very important whether we've got 50% of the vote or not. So in fact, I don't know as much as I ought to about civics, but some states you cannot win an election with a plurality. We had the example in 2020, I believe it was, with the Georgia vote, that we had 3 candidates running, or maybe it was more than 3, and none of them got more than 50% of the vote. So they had to have a runoff in January to decide who would control the Senate, right? I think that was how that was running. In any case, though, that makes it something that makes sense for us to talk about our hypothesis here being something about having 50% of the population be one party or having more than 50%. Okay. So I know that what makes sense logically is to say less than or equal to 50% on one side and then greater than on the other side for these hypotheses. But it's just logically simpler to be talking about having the proportion be equal to 50%. Okay. All right. So in any case, though, what did I say here? Yeah. So if we said something about, if we took a survey of 152 voters, oh, I didn't mean to do that. A survey of 152 voters, and we found out that 83 were in favor of something or were going to vote for a certain candidate, then we would find out from our survey, which is a sample, that we have 54.6% of the population, which is more than 50%. But then when election day comes, you're not going to have just that sample voting. It's going to be hopefully a large portion of the population showing up to do the voting. Okay. And so the question is whether our sample is strong enough evidence that we've got more than 50% of the vote. Okay. So the example that I made up here was simply this notion about talking about red versus blue. Okay. Right. So in this case here, I went ahead and created a function. This is a good thing for you to know about from Python stuff anyhow. But you see how it says def party. So it's defining a function called party. And so later in here, when I say I want to call the function party, it just goes up to the party function and generates a random number between 0 and 1. If the random number was less than 0.6, it's going to assign blue. And otherwise, it will assign red. Okay. The reason that I chose these numbers is that I don't know the exact numbers, but slightly more than 50% of the population vote Democratic in most elections. So I'm just kind of setting up that there. If you are a Republican voter and don't like that, well, I'm sorry. I'm just using this as an example. You can just go change all the colors if you want to. I don't care. All right. But in this particular thing here, we're just going to have it make up a sample of a bunch of voters and their parties are red or blue. Okay. And then I asked it to print them out. And how many did I tell it to do? We said n equals 20 for our sample size. So we're just doing 20, but you could totally do this with a huge number, right? And so if we do this and we get the proportion, remember it's the proportion in our sample, not the population, then we'll see these numbers come out here. So happened in this particular data run, I got exactly 60%. Let me go ahead and execute it again and just see if we get it again. See, the next time I did the data run, I ended up getting 50%. Okay. Sometimes I might get 65%, but it's going to bounce around a little bit. So notice that the way I did that was to take the list called voters, and I counted how many of them were blue, and I divided by the length of voters, which would just say how many voters we had in there. Okay, so that's how I was getting my p hat in that. Remember, p hat is the approximation for pi. It is not the same as your p value. I'm sorry, there are so many names that are close together. So then here in problem 4, I say, one thing you'll note is that the p hat almost never turns out to be exactly pi. And copy the code below and experiment to see when you seem to consistently get a number close to pi. I have not defined what I mean by close to. You get to decide that. And yeah, just experiment around with your value for n. Make it large, make it small, but do multiple data runs with the same n value and see when you think that you're getting consistently numbers that are close to 60%. Okay. And then insert a text cell below that and tell me what you found out. So now we're going to try doing the actual hypothesis test here. And the hypothesis test that I had earlier was running with a sample that had 60%. So now I've got it with 50%. I'm going to go ahead and rerun that, folks. So I'm going to rerun it. Oof, that's 75%, 70%. Ugh. 75, 40. Okay. So I'm gonna keep going here. I'm gonna leave it with a sample that had 60%. Okay. So then the thing I'm gonna do here is to have my count of the voters who turned up as blue just as X, and then the N is the number of voters total, okay? And then I'm using something called proportions z-test. I'm trying to put links here on the side to show you where I found these things, but you give it the value of your count, then you give it the value of the total number, and then this part that says value is going to be what's in the hypothesis test in the H naught, the 0.5 that we saw. Okay. And then your alternative, because we're trying to test to see if it's larger than 50%, we're going to say larger. Okay. But then when I run that, it comes out that we had 12 out of 20 voters were blue. Maybe I should have said belong to blue party. Okay. And that comes in then with a p-value of 0.181. 0.181 is not less than 0.05. So this is not strong enough evidence because we don't have a very large value for n. If we had a larger sample size, then we would feel more secure. I'm going to go back here and get a data run where we've got a bigger p hat. Can I get a here? I got one that was 0.7 this time. If I go run that again, then this time I got a p a p-value of 0.025, that's less than 5%. And so we would feel like that sample was strong evidence that we got what we wanted. Now, bear in mind, if you're doing this as a pollsters, companies that do polling research like the Pew Data Group, you don't get to go resample until you get the answer you want, right? I did because I was trying to make a point here, but you would go with the data you have and see what that tells you. If it turns out that you don't have strong evidence, then you say you don't have strong evidence. Okay. We probably ought to talk about, we'll do more about voting data later, and I'll try to talk about confidence intervals then. Okay. But anyway, so as you're reading along with this, notice that I've thrown in some extra stuff that I found in the examples here about how they format things. So take a look at that to see how that's working, right? So anyway, though, the data that I had before that was not very persuasive. I'll go back and make sure that you see something that's fitting the narrative here in a minute. But 0.025 is persuasive, but I think it was 0.181 was not very persuasive. You will have experimented to see what sample size that you felt like consistently gave you the consistently gave you numbers that were more than 50%. Okay. So what you're going to do here then, after you've found that out, is to take this data that was this code that was generating it, coming from a couple of cells here, okay, copy them down here and run it with a larger data run, with a larger n value that you found out about, and see if that's getting you a p-value that's small enough to be strong evidence. Okay. So leave the 0.6 in there and stuff, but play around with the n value. Okay. And then I went ahead and said here that if you want to go ahead and play around with this and try to understand what's going on better, I'll give you a little bit of extra credit if you'll go in and do this counting the red ones instead of the blue ones and making your hypothesis be about it being less instead of more, and work that out. Okay. So a little bit of extra credit there. All right, so here in problem 6, if you read in the vehicle data, I want you to determine whether there's strong evidence that more than 1/3 of the models are either compact or subcompact. From the day where we did pie charts, I think it turns out that between those two groups, you end up getting 35-ish%, something like that. But you can read that data in and have it do counts. And from the counts, then you can get an X and an N and run this hypothesis test. And because of the fact that your N value is going to be 45,000, yeah, you should probably end up with strong evidence. Okay. All right, one more thing here. Now, this one is referred to as the chi-squared goodness of fit test. Wow. Okay, that's kind of a mouthful there. Let me stop share on this real quick and check to make sure. Okay. I'm going to share screen and we're going to look over at the calculator for a picture here. So on the calculator, it has a goodness of fit test. And I'm going to ask it to draw for the data that it had. Okay, so this isn't the best of examples because you can't see the blue area that's getting colored in because the blue area is all off the chart here on the side. But We talked a little bit the other day about the fact that there are other distributions other than the normal distribution. And this is one of those that's lopsided, skew to the right. Is what we call that. And the chi-square goodness of fit test takes the counts for a distribution and looks to see if they're significantly different than what's expected. Okay. Let me go to the data I had here so that you can just see. All right. So the numbers that we had here were 13, 10, 15, 0, 13, 19, and 17. They were the counts that for an actual data run that we'll see on the Python there. But it was days of the week. Okay. And so what I did was to have a bunch of data that was generated, and here I zeroed out and didn't let any of the days of the week be, I think that was Thursday. Okay. But if we were randomly choosing and having them all be the same probability, then we would expect to get 1/7 of the total be in each one of those. And so that test that we ran with the calculator there was just testing to see whether the data looked the same. And in this case, we got a p-value of 0.0048. That's very small. And the chi-squared is just this distribution that looks at the difference between two things. And if the difference is a lot, then the area that's over here on the right-hand side is very small. And that tells us that we have strong evidence. Okay. So you don't need to know the mechanics of that other than how we run the test. So we're going to go back to the notebook here and see how we get the notebook to run that test for us. So in the example, first of all, I want you to see that the idea of the hypotheses is that you say your null hypothesis that you think is wrong is that you have the same proportion or approximately the same proportion in each of the categories you have. So in our particular thing, we're going to do some of the days of the week. So you want to say that the proportion of Mondays is the same as the proportion of Tuesdays, blah, blah. Okay. That they're all about the same. And then the alternate hypothesis is that at least one of those is a different proportion. Okay. So first off, we're going to generate some data where it is the same proportion. So I made a list here of the days of the week. I just abbreviated them with the 3-letter abbreviation so that it would be short and easy. And then for the variable I call population, which is just the number of possible things there, I told it to say, what's the length of days? So the length of the set that we're drawing from, okay? And then this n equals 10 is our sample size here, that we're going to draw a sample of 10 days. Okay, now I remembered as I was making this that I could do a neat trick. I had to play around with it to see how it would work. But if you don't see how to do this, you can instead write code where you just append onto the end of the list. But this is super slick when you can get it to work, right? So the thing I did was to say random integer 0 to 6, because that's how days will be numbered, 0 through 6. And I went ahead and inside of a square bracket put days of random integers 0 to 6. And then after that, I just wrote for I in np.arange of n. So that says run through the numbers 0 to n minus 1 and let I be each one of those, I doesn't actually appear in the calculation, but it will have the net effect that it will go 0 through 9. So it'll go 10 times through this loop and pick something randomly out of that days. It's kind of a neat trick to use for random sampling. I don't know that it's useful for many other things, but maybe. So anyway, I got it to print out our sample here. We're just getting a small sample, so this really isn't, I wouldn't think of as being very strong evidence of anything, but you know, and it printed out and you can see what those were. Now, the thing is, what we want is not really the sample itself, but a count of the sample. And so I wanted to introduce that trick there about using the loop because of the neater thing that I do down here, which is to say I'm going to make an array out of it. But the thing I'm making an array out of is a list. And the list is that I'm going to take my sample and count the number of things in days of I. Okay? Days, square bracket I. And then I'm going to have the I run through 0 to 6. So that will run through and say, hey, how many Mondays do you have? Hey, how many Tuesdays do you have? And so forth. So it's going to make it into a list. And then I use the np.array to make it into a numpy array, because if I don't, I get certain kinds of errors. Okay. So anyway, that shows you what observed will come out to be. And so it has 2 Mondays, 2 Tuesdays, 2 Wednesdays, 0 Thursdays. That's weird. 1 Friday, 2 Saturdays, and 1 Sunday. Okay. But then the expected number, okay, for the expected number, I'm going to generate it the same way with the 4i in the range up to the population size. But the number I'm going to put in here is sample size divided by population size, okay? Because we're just expecting the same number of them in each one. And so the number I get out of that is about 1.4 for each one of the entries. And then the hypothesis test, remember the hypotheses are pi1 equals pi2 equals pi3 equals up to pi7, but they're all equal, versus, oh, that was supposed to print better. Sorry, I am a little bit of a weenie about these things. I want it to look right. Okay, versus the alternative that one of them is different. Okay. And when I ran that, I got a p-value of 0.857, okay, which is very large. And that tells you that this is not strong evidence that we have something that's different from the uniform distribution, okay? So you should rerun it, like just get a different data run, maybe also come up here and do a data run with a larger data run, okay? Because n equals 10, pretty small sample, okay? Oh yeah, and that's what I tell you to do. Haha, time for you to try it. Copy the code, and you're going to take stuff from several cells and put them down here. But I'd like you to try this with something different. Maybe pick out 6 colors or 4 fruits, or, you know, anything you can think of that's going to be relatively neutral, okay? And that you would maybe have showing up randomly. And so you can think about them as car colors or fruit that's served in the cafeteria or something. I don't know. All right. But produce a relatively large sample. So what I would say is take my code and take the pieces and pop them into one single cell and get rid of some of the printouts portions of it because they're not going to really help you that much. But get them to run in a single cell so that you get your p-value printed out, and then go back up and change from your list of days of the week to some other list, okay? And then run it to see that it's going to work. And then play around with that p-value, not p-value, n value, sorry. So play around with your sample size until you see when you feel like you're getting, you feel like you're consistently getting results out of it that are saying that this is not strong evidence, okay? P-value is more than 0.05. You probably won't have to take a very large sample to get that, but anyway, so that's problem 7. So for the next thing I wanted to do, I wanted to give an example where you did the opposite, where you had strong evidence that it was different. So I ran down through here and just put the same code in. Oh, by the way, you can copy this code and put it up there, but don't do the thing that I did here, okay? You would want to just remove this one big piece. So anyway, I came down here in this with the days of the week example still. I made my sample pretty large, 100 of them. And I went ahead and did that same thing as before of generating the random sample. But then I went in here and I pulled out the Thursdays. And then I made a joke. You get nerd points if you get the reference, but I have a suspicion nobody will get the reference. But this is something that I found, and I thought that I forgot to give you a citation for it. I will put a citation in it later. I can see where it is on my tabs. Anyway, though, I just cut out all of the Thursdays, and then my observed scores, I did the same trick as before. And then my X needs to be equal to observed over population. Oh, you know what? I need to fix this a little bit. I need to go ahead and change and say now my population is going to be the length of observed. That's not my population, sorry. That's my sample size. My sample is going to be the length of the observations. I hope that makes sense to y'all, because since I cut out the Thursdays, that means I need to resample and figure out how many of them we actually have there, okay? And then as we run along here, sample length observed, and yeah, so your X will be the sum of those observations divided by the population. Is that right? Yeah, right. And then we create the expected value. Whereas before we had, we have the expected value there, and we're just going to get our counts going across on these. I feel as though I did the wrong thing on that. Okay. Sorry, folks, I'm thinking about this as I go through, and I'm trying to make sure that they make sense. So the observed is going to be the counts from the population that have each of these things. Then the expected would be the uniform number of them, okay? And it is the sum of the observed and divided by the population. Okay, yeah. Okay, this did not need change at all, sorry. Then we're going to hand it off to the hypothesis testing thing that we've got. that was coming out of scipy.stats, right? So it's going to take the observations and the expected observations, compare them, and see what's going on there. I went ahead and told it to read out the chi-square and the p-value. The chi-square turns out to be something that some statisticians need to look at. So I mentioned it in here just in case you ever see that come up from some other class. But what we're really looking for is the p-value for it, and we get that to print out. Okay, so hope that makes sense. With the data run that I had last, I ended up getting a p-value of 0.0048. So that's like that's like 0.5%. That's way less than 0.05. Okay, so that means we've got pretty strong evidence that when I yanked out all the Thursdays from the sample, that meant that the sample was no longer uniform, which is not surprising. Okay, and then I ask you here for problem 8 to go back in, copy that code down there and do the same sort of thing. Yank one of them out of there by deleting, and show that you're going to get a p-value that is significantly less than 0.05. I would say play around with it a little bit and see how big of a sample you actually need to get that to happen, just kind of as a curiosity, okay? But once you got that to go, then put in a text block and just say something about your conclusions, what observations you had. Okay. And then last thing, for a little bit of extra credit here, try either number 7 or number 8. But if you go figure out how to do the group by trick from data frames to do that, I'll give you a little bit of extra credit for the effort of doing it. Okay. If you're saying, yeah, I don't get that at all, don't worry about it. Later, we will do stuff that's related to that, this sort of idea, and we'll see it better then. Okay. But this is just, if you get a little bit ahead, you're a little bit ahead. Okay. That's what I'm looking for you to do. Get that in, and I will see you all in class. Guess I have to actually stop recording, huh?